So we know that an integral is related to the area of a graph, the visual connection between those two. But what we want to do is talk about the difference between net and total area, because there are two differences. All right, so net area versus total area. So how are those two things defined? We have been working on net area. Net area is defined as the integral from a to b of the function f of x dx. So the definition of net area is what we've already been working on. Let me get some good parentheses here. Okay, there we go. So starting at A, ending at B, adding up all of the area between the function and the x-axis, and you could end up with a negative answer if more of the majority of the region was below the x-axis. All right, versus total area. That is also the integral from a to b, but instead of using parentheses, you use the absolute value. That answer will always be positive, and it will take all of the negative area and make it positive, therefore coming up with a larger answer than what you would have with net. When would these two be the same? Would there ever be a case? Yeah?
When you have a function that never goes negative.
Okay. When a function is exclusively above the x-axis, okay, or equal to the x-axis, then these two things would be equal. But if there's any portion of the function that does dip down beneath the x-axis, your net is going to be less than your total. Now, if you have your calculator, you can just put the absolute value in your calculator, like type it in as part of your Math 9, and go on your merry way and be done with it. Those are easy. Without the calculator, we want to think of it geometrically. So that's what we want to talk about today. Okay, so what's the difference between net and total area for this function? All right, and let's look at the function 2 cos 2x. And let's look on the interval 0 to pi. For me, it always helps me to have a visual representation. Okay, 2 cos 2x. I know that cosine is shaped like this. I know from the design of the function that the first a in the front, the number 2, tells me that the amplitude will be 2. So I'll have 2 as my high and negative 2 as my low. So my range would be from negative 2 to 2. I also know that the second 2 affects the period. The period of the graph is where the end of the first cycle happens, and period in trig for sine and cosine is always 2 pi divided by b. In this case, 2 pi divided by 2, therefore pi is the end of the period. And so just a quick sketch, a quick understanding of this, I can see that I've got equal parts of positive area, but then I also have a section of negative area. And so this is going to give me a net area of 0. I don't even have to do any calculus because I just understand the way that the positive and the negative area will cancel each other out. Now if I want to draw total area, my total area will take that negative section. Okay, well here's the positive section. I have a positive section here and a positive section there, still 0 to pi with an amplitude of 2. But it's going to take the negative section and it's going to put it above the x-axis. So now I'm going to have not an answer of 0, but I'm going to have all positive area. So I'm going to approach that doing an antiderivative to find that area. So I want to go, I could do a couple different things. I know that this is split up into pi fourths, pi halves, 3 pi fourths. One way I could approach this is I could just find the area from 0 to pi halves. And once I have the area from to pi fourths, 0 to pi fourths, once I have that, what could I do to that to find the total amount of area? Multiply by 4. There are 4 such sections of that, okay, replicated. And so that would be one way that I could approach this. Okay, you would say, all right, 0 to pi of the absolute value of 2 cos 2x absolute value dx is the same as 4 times the integral just from 0 to pi fourths, pi fourths of regular 2 cos 2x in parentheses dx. So using some geometry, I can eliminate the absolute value. And then I can work on solving this by hand. So 4 and 2 make 8. Those are both the coefficients. And then the antiderivative of cosine is sine 2x. And the chain rule would normally require me to multiply by 2. But I'm doing antiderivative, so the anti-chain rule would require me to divide by 2, plus the constant of c going from 0 to pi fourths. So 8 is the coefficient out front. That's the combination of the 4 that I originally had, and then the 2 is the amplitude. So now we've got 8 times 1/2 sine of pi. Can I do pi? Okay, if I write pi halves plus c, because that's 2 times pi fourths, minus 8 times 1/2 of sine of 0 plus c. And then we simplify. 8 times 1/2 is 4. The sine of pi halves is 1. The c's cancel out. Minus 4 times 0. So 4 is the total area of that graph. Okay, I don't need a calculator to help me out with that. Okay, next one. All right, find the total area. Under the cubic function, x cubed, on the interval -1 to 2. Okay, the total area under the cubic. All right, so let's get a picture of our cubic. Our cubic is going from -1, +1 to 2. So I have some negative area and I have some positive area. what I need to do is I need to take that negative area and make it positive here, because I want the total and not the net. So we're going to set up and always get points. You will always get points for simply setting it up in an absolute value. Okay, we want to find the total, which is defined as the absolute value from -1 to 2. Now you can do this in a couple different ways. I can separate this function from -1 to 0 of x cubed dx. But I know that if I go from -1 to 0, I will get a negative answer, because -1 to 0 is beneath the x-axis. So what could I do, using the properties from yesterday, to make sure that that turns out to be positive? Okay? Okay, so I'm hearing different things. There are different answers you can have. One, and I'll cover all of them, is to flip the bounds and go from 0 to -1. Go backwards. That'll make it positive. And then add to it the stuff that's already positive. So I could do it that way. Okay, another way to do that is to recognize that geometrically this area is equal, in a net sense, in an absolute value sense, to the 0 to 1. And so I could also, I think that was Abigail, you were going on doubling it, I heard, right? So you could take the area that's from 0 to 1 and double it. And then take the area from 1 to 2, and then that was just fine. You just need a single value of that. That is another way to set that up. Can anybody think of a different way? Is there another way, besides switching the bounds on the -1 to 0, is there another way to just make sure that it's going to be positive? Yeah, I can't integrate with absolute values. So yeah, we start with absolute value. I could just throw a negative in front of it. So I could leave it from -1 to 0, which I know is going to, if I left it alone, it would be a negative answer. I can put a negative in front of it to make sure that that would be positive. So there's a couple ways that you could approach that, and any one of those would be fine. You just have two separate integrals, and then you'll do the antiderivative of each piece. I think I'm going to do this one. Okay. All right, so that's going to be my work. Go from there, but you could do different. All right, 2 times the bracket, the antiderivative of x cubed is x to the 4th over 4, plus the constant c going from 0 to 1, and then adding to that, also x to the 4th over 4 plus c, this one going from 1 to 2. So I will have 2 times 1/4 plus c minus 2 times 0 to the 4th plus c. And then my second antiderivative would be 16/4 plus c, plugging in 2, minus 1/4 plus c. And then we're going to simplify. So this one is 0. The plus c's all and the minus c's all cancel out. And so I will have 1/2 plus 4 minus 1/4. So that's 4 1/4, or 17/4. Okay, another thing that you would use multiple integrals for is a piecewise function. So if you want to find the area for the integral from -1 to 3, the arrow on that integral for, okay, and the function may be defined in separate pieces. So that means you have a parabola as long as x is less than 1, and then it switches to a square root as long as x is greater than or equal to 1. So this would be another case where you would use the addition of two separate integrals. So we think about the graph. A parabola going up to x is 1 is going to stop. Oh, I don't like how that is turning out. Problem is here. Ugh. Okay, better. All right, stopping there, but I am going from -1 to +1. So here I would want this much area connected for those two. And I do see that those are symmetric. And then I'm going to switch, okay, at the equal to, and now it switches to the shape of a square root. And the shape of a square root is going to be heading off in that direction. And I want to go up to the number 3 on that one. And so that would be a different shape of area up to here. So all of this area is positive, so we don't need any absolute values. But I can use symmetry to help me out. So again, I've got a couple different ways I could do this. I could do the yellow section. I could go from -1 to 1 of x squared dx. Or I could also go from just 0 to 1, and I could make sure to double it. So it is your choice. I usually prefer, if I can use 0 as one of my bounds, I love to use 0 because it makes the whole plugging in thing so much easier. So that will cover the yellow section. The green section has to be done from 1 to 3 of the square root of x dx. So that would have to be done that way. And then you would evaluate, so those two things are equal to each other. So that would be 2 times the antiderivative of x squared, which is x cubed over 3, plus c, going from 0 to 1. And then the second antiderivative of the square root of x is x to the 3/2. So I'm adding 1 to the power, divided by 3/2. And I don't prefer to divide by 3/2, and so rather than dividing by 3/2, I prefer to multiply by 2/3, multiply by the reciprocal instead. And that will go from 1 to 3. And I'm not going to take the time to plug those in specifically.